This begins video 6 of section 4.4, and we're going to pick things up with number 26. And on this question, we're going to do it two different ways. We're going to take the dimensions of this rectangle xy, and we're going to create two different cylinders. So in part A, all we're going to do is roll up the piece of paper, or the whatever it is, sheet metal, and create a cylinder. And so part A says that the rectangular sheet has a perimeter of 36 centimeters. So we know that the perimeter of this is 36. And x by y rolled into a cylinder. What values of x and y? Largest volume. So focusing on A here, let's think about the volume. So in general, in a cylinder, we know that the volume is going to be the area of the base, pi r squared, times the height. So now we're going to have to convert this, I think, in two stages. So first of all, the height is in fact going to be y. And now we've got to figure out what the radius is. So focusing on this tiny cylinder up here, we want to know this line segment, the radius. So if we look at the distance around the cylinder, the circumference, we know that has to equal x because we rolled this up, and so the distance around the circle is x. Circumference we know is 2 pi r, which equals x, which means we can rewrite r to equal x over 2 pi. So now I can plug that in, and I get volume equals pi r now becomes x over 2 pi, the quantity squared. Alright, so now I've got volume, but I still have two variables, so I still need to convert x to y or y to x. And I think I want to convert the y to x. And that's where we go back to our rectangular sheet, and we realize the perimeter is 36. So we know that 2x plus 2y is 36, or x plus y equals, divided by 36 would be 18. So let's say y equals 18 minus x. And so now we can substitute that in, and the volume becomes pi x squared over 4 pi squared times 18 minus x, which, simplify one more time, pi will cancel out one of these, and I'm left with, looks like x squared times 18 minus x all over 4 pi. And we'll probably want to simplify this a little bit further, but we'll save that for possibly another video. So there's my volume equation. Take the derivative, find the max, find the min. Well, not the min, just the max. Okay, so now let's do it again. And this time we're going to create our cylinder in a different way. We're actually going to take it, and if we rotated that rectangle around the center point, we would, shave out or carve out a cylinder. So volume is pi r squared times h. So as we look at this, we try and figure out what we know, and the height of the cylinder would still be this value, which is y. We still have pi, and so now I need to know the radius, but the radius is simply x. So this becomes a much simpler problem. So we have the volume, but we still have it in terms of two variables. So now I need to convert again. I've already done the work to find the conversion. So now we simply get pi x squared times y, which is 18 minus x. And so now volume equals pi times negative x cubed plus 18x squared. And I would just need to now take the derivative. All right, moving on. number 29. It says, show that f of x, given here, cannot have a local maximum for any value of a. So show that we do not have a local maximum no matter what a is. So nothing to set up on this problem, might as well just do it. So if I want to talk about local maximums, then it sounds like I need to take a derivative. And again, I'm taking the derivative with respect to x. The a is a constant. And so that gives me 2x minus, because, again, look at this as x to the negative 1. So the negative 1 comes down, making it negative a x to the negative 2. And simplify 2x minus a over x squared. I'm going to make it into a fraction. So a common denominator, he gets the x squared over x squared, making it 2x cubed minus a over x squared. So, looking at critical values, the derivative equals 0 when 2x cubed minus a equals 0, or x cubed equals a over 2, or x equals the cube root of a over 2, for whatever that's good for. I also should consider the derivative being undefined, and that's going to happen when x equals 0. But that's not going to be for some real interesting reason. It's not because it's a corner or a cusp making a max or min. It's simply because if you look back at the original problem, I can't let x equal 0 in the original problem. So the reason we have an undefined derivative is simply because we have an undefined value. In other words, we have a discontinuity. We have no point at 0. So we have an asymptote or a hole, and then you can't take the derivative at an asymptote or hole. Okay. So now we just need to put our values on a sign chart as best we can. And I'm going to go ahead and throw 0 on there because my signs can still change at my slopes can still change at a discontinuity, even though it wouldn't be a max or a min. And that goes back to thinking about, asymptotes. If I have a graph that approaches an asymptote, its slopes are positive. As I leave the asymptote, my slopes are negative. And so notice I've changed increasing to decreasing without ever having a local max or min. So that's why we still need to consider these 0 or the undefined points on our sign chart. So let's see what else we can do here. 29 for any value of a. Okay. So the question becomes, where is a root 2? So if a is a positive number, then that would put my value someplace over here. So let's go ahead and see what happens if we place it over here. So going to my derivative, again, assuming a is a positive number, I plug in x is less than 0, so x is negative number. Negative cubed is negative minus a over x squared, so x squared is going to be positive. So I'm going to get a negative minus a positive, so it's going to become more negative. So negative divided by a positive is negative. Assuming that a causes this to be bigger than, well, let's do this. Let's plug in a number that's barely bigger than 0. So we're going to plug in like 0.00001. The bottom is positive because it's squared. The top becomes 2 times 0.000001, which is very small. So that's basically 0 right here, minus a. Assuming a is something bigger than 0.0001, then we get a negative value right there. plug in a super large number, like a billion, and I get positive over positive. So we've looked at the case where a is a positive number, and we've got this as an answer. So it said show that we don't have a local maximum. So in this case, where a is greater than 0, we can clearly see no maximum. Well, what if a is actually a negative number? Then that would mean this sign chart is no longer quite right, and now that point should be over here. And if we do our sign chart, I don't think we're going to find anything changes. So I plug in a super negative number to my derivative, which is here. Let's put a box around it so we can find it. I put in a super negative number, square it, the bottom's positive. Super negative number cubed minus that negative number, the cubed is still going to win, so this is going to be more negative than that's positive, and I'm going to get a negative. Plug in a number, any number bigger than 0, like a billion, and we can see that that's going to be positive. And then we're going to plug in a number really close to 0, like negative 0.00001, which is going to make this stay negative, but very tiny. And a negative makes positive, because we're assuming a is negative. So we're going to get a positive value. So once again, we're looking for maximums, and we don't see any place where we go from positive to negative. We just go from negative to positive, and then positive to positive. So when a is less than 0, no maximum. Only thing left, I guess, is a could be 0 itself, in which case, if a is 0, then what will that mean for us? If a is 0, then really what seems to be happening is this point, if a is 0, actually becomes my only critical value of 0. And we know x can't equal 0, so we know that we'll never be plugging in 0 in this case. So if a equals 0, we actually have no max or mins, we only have an asymptote. So long story short, no maximum. Okay, let's squeeze in number 30 to this video. What values of a and b make that function have a local maximum at x equals 1? So we want to max at x equals 1. X equals -1. And a local minimum at x equals 3. Okay, so we just need to ask ourselves a question. If we have a maximum at x equals -1, then what do we know is happening at x equals -1? We know that we've gone up and then down, making the slope at -1, 0. So if I were to take the derivative, I get 3x squared plus 2ax plus b. And I know if we have a maximum at -1, that would mean that when I plug -1 into my derivative, it should equal 0. -1 squared is 1. Minus x is -1, so minus 2a plus b. Or I could say -2a plus b equals -3. Alright, so I have an equation with an a and a b in it. No way I can solve that by itself. But I also was told that there's a minimum value at x equals 3. So when I plug x as 3 into my derivative, I know its slope has to be 0. So that gives me, plugging in 3 squared is 9 times 3 is 27. 3 times 2 is so plus 6a plus b. Or 6a plus b equals negative 27. So I still don't have the answer, but what I have are two equations with an a and a b, and so now I can solve with a system of equations using a substitution or linear combination and solve for a or b. A and b. So I'm going to leave you to do that. Number 30 is 30b is the same question, except this time it says we have a local minimum at 4, so we would do exactly what we just did. But they also tell us we have an inflection point at x equals 1. And so an inflection point means we need to consider the second derivative. So let's find the second derivative. And just in case you're confused, part A and B here are completely different questions. It's not like the answers we find here carry over to B. We're just using the same information. So the second derivative, because we need to address that inflection point, would be 6x plus 2a. And if I have an inflection point at x equals 1, we know that when I plug 1 in for x, my second derivative should equal 0. So I get 0 equals 1 went in for x, so that's 6 plus 2a. I get a is equal to negative 3. So combine that information with, again, we got to look at our first derivative and the fact that we have a, in this case, a minimum at 4. So we can create an equation that's going to look like one of these. And then I already know what a is, so I can plug that in and solve for b. Okay, so this will be the end of this video and possibly the end of section 4.4. I may leave the rest of them for you to finish yourself.